Hello, my name is Hannah Hayes, and I'm studying biochemistry and working under Dr. Peter Kroll to investigate the reaction mechanisms during cross-linking and pyrolysis of Ceracet PVZ20. So polymerized ceramics are stable at really high temperatures, which makes them useful for aerospace and military purposes. Ceracet PVZ20 is a polymethyl vinyl silazine and is one of the most used precursors for SiC in ceramics. By using molecular dynamic simulations, we were able to investigate these reactions at an atomic level. This scheme shown here shows the different parts of the polymer. It contains this fragment here that has silicon, hydrogen, and a methyl group, as well as silicon, a methyl group, and this vinyl group, which is in 20% abundance. As you increase the temperature, the ceramics are formed. And this image over here on the bottom just shows a section that highlights these vinyl groups here. This image in the middle just shows two different cross-linking reactions, and this image on the right shows the polymer after pyrolysis. For this project, we use ab initio molecular dynamics, and this is used for the simulation trajectories. This project was started by my supervisor at the beginning of last year, and performing these simulations can take weeks to months. So the data was collected and these simulations were then provided to me, and I investigated the cross-linking and pyrolysis of different models. So all of these models were under periodic boundary conditions. In these simulations, we mimic the use of a catalyst by first removing one proton from each vinyl group on the end carbon here. And this was in order to mimic the catalyst again. We were able to isolate the important atoms involved in the reaction for clarification, but all of these images here are selections from the larger models. This first image here for the reaction shows a cross-linking reaction, which is a hydrosilylation reaction, which, as you can see here, this hydrogen atom leaves the silicon atom, and then this three-coordinated silicon atom interacts and binds with this vinyl group here, creating this cross-link reaction. The next reaction seen is this polyaddition reaction between two vinyl groups. As these radicals move closer together, you can see that this linkage is formed. The last reaction typically seen in these cross-linking reactions is a polyaddition between an ethynyl and a vinyl group. This ethynyl group is formed by a proton migration in an earlier step, but it's not shown here for simplification. And as this triple bonded ethynyl group interacts and moves closer with this vinyl group, the linkage is formed. For this pyrolysis reaction, we first observe a ring opening reaction where this hydrogen atom leaves the silicon and then moves to a neighbor silicon, and the nitrogen silicon bond is broken, opening the ring. This was from a larger Si15 ring model. The next ring opening reaction is seen from the hydrogen instead now leaving from a nitrogen instead of a silicon. And again, the nitrogen silicon atom is broken, opening the larger ring system. We also see ring formation, smaller rings being formed within the larger ring system. We see this here with this nitrogen interacting with this silicon over here, forming a four-membered ring. However, four-membered rings aren't especially stable, so pretty soon after, this four-membered ring breaks open and the silicon then bonds with a neighboring nitrogen and forms a six-membered ring. The last reaction that we see currently is H2 formation. We see a hydrogen leaving a nitrogen and a silicon here, and H2 gas is being evolved from the system, which is a very common reaction known to happen during pyrolysis. So it was really interesting to see that through a computational method. So this project utilized the ab initio molecular dynamic simulations in order to study the cross-linking and pyrolysis of these different Ceracet PVZ20 models. The two principal reactions seen during cross-linking was the hydrosilylation reaction as well as the polyaddition reactions. The early reactions seen in pyrolysis were the ring breaking, the ring formation, and the formation of H2, and this is still in progress. So we already seen the indication of methane being formed, but this is something that we hope to investigate further.